Hello, I'll be presenting a review of sharpness aware training schemes across architectures and datasets. Deep neural networks are prone to overfitting, which means that the test accuracy is less than the training accuracy. This difference is known as the generalization gap delta. Also, modern DNNs are complex loss functions with multiple local minima. This makes it challenging to train DNNs to converge to an optimal minima at which delta is less. Intuitively, a flat minima in a low curvature region in the loss function will result in a minor increase in loss upon perturbing the model parameters. However, traditional optimizers such as stochastic gradient descent do not account for the sharpness of the minimum and often converge to a sharp minimum. The first sharpness-aware training scheme is the sharpness-aware minimization SAM, wherein the model weights W are perturbed to W dashed within a ball of radius rho. The loss is recomputed at W dashed and the weights are perturbed and the weights are updated using the perturbed gradients. Following the algorithm, we can see that two forward and two backward passes are required per weight update step. The perturbation radius rho is the hyperparameter of the algorithm, and it is expected that when rho is increased, we are checking in a larger neighborhood, and hence the generalization gap delta must be low. However, it has been seen that the loss function remains flat over 95% of the dimensions. So sparse perturbation is sufficient. So we use a mask M to perturb the weights selectively rather than perturbing all the weights. The algorithm for SAM is the same as SAM, with the only difference that now we perturb only a fraction of the weights to W dashed within a ball of radius rho. The computational overhead of SAM is much less as compared to SAM, since two forward pass and two backward pass are incurred only for a small fraction of the parameters. SAM also depends on the type of mask employed. Top-K mask perturbs those parameters which have the highest gradient values, and a random mask only perturbs the parameters selectively, which are randomly chosen. Third sharpness-aware learning scheme is the gradient norm penalty, wherein a gradient norm-based penalty term is introduced in the loss function. Lambda, the hyperparameter, is the strength of the gradient norm penalty term in the loss function. So GNP discourages the model from converging to a sharp minima where the gradient norm is large, and it is our expectation that as delta is increased, as lambda is increased, delta must reduce. This is the baseline study where all the algorithms have been trained on different models and datasets. It has been seen that SAM performs the best on ResNet 18 CFAR10 and ResNet 50 CFAR10, whereas GNP performs the best on ResNet 18 CFAR100. SSM with the random mask performs the worst in all cases due to the random selection of dimensions. The number of hypotheses required for convergence of all sharpness-aware schemes is less than that of SGD, and the time per epoch of sharpness-aware algorithms for ResNet 50 is 2 to 5 times than that of SGD, which means that these algorithms are not scalable to deeper networks. SAM is the most efficient, and SSAM random is the least efficient on an average. This is the tabulation of the baseline study. Ablation study has also been performed wherein the hyperparameters of each algorithm have been varied to check for the generalization performance and the computational efficiency. As the rho is increased for SAM, delta reduces. As lambda is increased for GNP, the delta reduces. And for SM with either kind of mask, top and random, as the mask ratio M is increased, the generalization gap delta reduces because more is the M, larger the number of dimensions considered in the weight update step, and hence higher the probability of finding a flat minima. More accurate is the algorithm. This is the tabulation of the ablation study that has been performed for all algorithms on ResNet 18 and CFAR10. So in conclusion, we can say that SAM has emerged as the most trustworthy considering both the generalization performance and computational efficiency. For ResNet 18 CFAR10, SAM reduces the generalization gap to as low as 0.26%. However, owing to the computational overhead of these techniques, they are limited to shallower models like ResNet 18 and not really to deeper models like ResNet 50. Thank you.